So in the last lecture, we have seen how to find root of an equation using, how to approximate root of an equation using bisection method. Alright. So in this class, let us explore two more methods to approximate root of an equation. Okay. But before that, I would like to introduce transcendental function. Alright. And before that, you must know what is an algebraic function. And before that, you must know what is an algebraic number. So if you know what is an algebraic number and transcendental, you can easily identify an algebraic number and a transcendental function. Suppose if you have a number, for example, I have to, if this is a root, a polynomial, not just you take some arbitrary number, not real number. Okay, so the real number is said to be algebraic number if there exists a polynomial p of x with real coefficients. So with real coefficients, we must find a polynomial so that this a is a root of the polynomial. Sorry. So there must exist a polynomial with rational coefficients. Okay. So tell me a real number which is algebraic. For example, suppose if I take x square minus 2 equal to 0. So what are the roots of this equation? The roots of this polynomial. Here the roots are nothing but plus root 2 and minus 2. So we are going to treat now as per this definition, this root 2 and minus 2, these are algebraic numbers. Okay. So similarly, what can you say about root 5? Is it algebraic or transcendental? You just say whether it is algebraic or not. Can you find a polynomial with rational coefficients? For which this is a root. Yes, it is possible. X square minus 5 equal to 0. This is the polynomial. If you see the coefficients of the polynomial, are nothing but 1, 0 and minus 5. What I mean, this is the coefficient of x square, this is the coefficient of x, and this is the coefficient constant. Alright, so the coefficients here are real. So therefore, this root 5 is a root of this equation, therefore it is an algebraic number. Alright. How about 3 to the power of 1 by 5? What do you think? Is this 3 to the power of 1 by 5? Is it an algebraic number or a transcendental algebraic number? It need not be of second degree. You can take third degree algebraic number. Okay. So what is the polynomial for which this is a root? Can you give me a polynomial for which this much? Yeah. X to the power of 5 minus 3. So here if you observe that the coefficients of the polynomial, they must be from rational numbers. This is the condition we have here. The coefficients are from rational numbers. Alright, and we can see that 3 to the power of 1 by 5, the root of 6 is therefore the algebraic. Alright. So now numbers which are not algebraic, we call that as they are transcendental. So transcendental number is nothing but a number which is not algebraic. Okay. It means if it is not a root of a polynomial with rational coefficients, that number is a transcendental number. For example, can you give me some number which is not a root of a polynomial with rational coefficients? Yeah, I'll tell you. So if you take the number e and the number 5, these are transcendental. transcendental numbers. Alright. And there are some other numbers like e power 5. Okay. And if you see root 2 to the power of root 2. Okay. Similarly, ln2. These are all transcendental numbers. Okay. You cannot find a polynomial with rational coefficients for which these guys are roots. You can't say that x minus e equal to 0. This is a polynomial for which e is a root. But okay, this is a polynomial for which e is a root. But what are the quotients here? Quotients must be rational numbers. Is e a rational number? It's not a rational number, it's actually irrational. Okay, so the quotients we want rational numbers. Alright. So you don't have a polynomial for which polynomial with rational quotients for which it's easy. Alright. So this is how the algebraic numbers and transcendental numbers are defined. Now let us see what are algebraic functions and transcendental functions. Now algebraic function, it means there we define it like in terms of numbers we said it is a root of the polynomial with rational coefficients. But here our function you may take it as y of x equal to f of x. We want to say this function is an algebraic function. It has to be a root of this polynomial in terms of that is p1 of x into y power let me take some second example of general pn plus pn minus 1 of x into y to the power of n minus 1 plus blah 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 plus p1 of x in y plus p0 of x equal to 0. Where I hope you know what to be meant by this pi of x. The pi of x is the polynomial in x. And you know how a polynomial in x is that is subject to a0 plus a1x plus a2x squared plus and so on a into x power. This is how the polynomial in x power is. Alright. Now, if you want this function to be an algebraic function, this has to be a root of some polynomial like this. A polynomial in terms of maybe as an example, we can talk about y equal to 1 by square root of 1 plus x. So let me talk whether it is an algebraic function or a transcendental. So if you claim that it is an algebraic function, it must be a root of a polynomial like this. Okay. So let me try to explain this way. This one can be written like this: y square equal 1 by 1 plus x. Alright. Now this implies 1 plus x into y square minus 1 equal to 0. Yeah, now I got a polynomial in terms of y and it is in this form. Right? If you observe the form, what I have here is it's like some see, you don't take this pn of x, it means it is an n minus 1 degree polynomial. It's a polynomial of some finite degree. Okay. So it is just a notation, right? So here I have some polynomial p of x y square plus q of x y plus r of x equal to 0. Alright, if you ask me what is p of x here, so let p of x is actually 1 plus x and q of x is 0 and r of x is nothing but minus 1. So now this is the polynomial in terms of y and for which this function is a root. Okay. So therefore we can see that this function is an algebraic function. Alright. So simply saying, if you want to have find whether the function is algebraic or not, you just see whether it is formed with an algebraic operation or not. Algebraic operations, I mean, you can add, you can subtract, you can multiply, and you can divide. Okay, so these are the algebraic operations we are taking. So let's say if I take a polynomial like x squared plus 1 or x squared plus x plus 1, this is an algebraic function because what I'm doing is I'm multiplying x and x here, I'm writing x squared, and I'm adding the terms x squared, x 1. Right? I'm writing this expression. So this function, you take this as a function, it is algebraic. Alright. So similarly, you can actually take 1 by x. It's also an algebraic function because just I'm dividing it with the help of this algorithm. Okay, maybe okay. If you want me to fit this guy in the definition, yeah, we can put y into x into y minus 1 equal to 3. So this 1 by x is the root of this equation. Alright, so it is fitting with the definition also. So whatever things you see with x squared, and even power, negative powers are also allowed, and also the square roots are allowed. Power 1 by n is also allowed. Right? So it's algebraic. But now what is a function? It's not an algebraic. And we have some examples of a function which is not an algebraic function. And that's what we define it as transcendental. So now you can actually think about exponential functions. Okay, so this is the definition for algebraic function. Right. So now I hope you understand what is an algebraic function. So y is root of this is 1, 1, then y is an algebraic function. Okay, so this is the definition for algebraic. Now transcendental function is nothing but a function which is not algebraic. The definition is simple. Let me write a function which is not okay. So example is an example. You can take see, we know e is a transcendental number, right? So from there you can say e power x, also sin x, like cos x, okay, and logarithmic functions, log x. Like all these functions we call them as transcendental. But not only this, but these are just some examples. I'm not listing all transcendental functions. I just listed some of them. Okay, you can take tan x, tan inverse x, anything, sin inverse x, alright, and so on. It means there are many. It's not only the finite list. Okay, okay. You may ask me why we are discussing this transcendental. Because for algebraic functions, you may have some procedure of the second degree, third degree. In special cases, we can discuss even for n degree also to be the formula. But if it is an equation, suppose if the function involves transcendental function, for example, x into e power x minus 1. Okay. So this is the function you have. Now you're asked to find root of f of x. And if you observe this f of x, it is involved in transcendental function. Okay, it is involved in e power x. Alright. So we do not have a specific procedure again to find exactly the root. I'm not talking about approximation. We have methods to approximate it, but obtain the exact. So how do you? Maybe in graph also you can locate it, and through graph also you can locate the point, and you want to list that number, you can write this rational number or a natural number is fine. You can directly see. But if it is kind of an irrational number, I want the proof. Then I'm gonna see that power of minus 1000 kind of thing. Graphing also may not help us much. Okay. So I hope you understand what the algebraic functions and the graphing. Okay. So now let us discuss about two more methods to find the root of a thing, to approximate the root of a thing. Alright. So that equation it may be a polynomial or may be a function involving transcendental. Alright. And suppose if you are asked to classify algebraic and transcendental function, given some list, you must be able to classify it. You must be able to separate. Okay. Like one can ask it as an object question. Given four options, which among these function or which one is the algebra? You can have some kind of question. This is four. Right? Now let me discuss the other two methods. So yesterday we have some bisection method, right? Now we are going to see the regular Falsi. It is also named as false position also. So now here the idea is, suppose if you have some graph, it's the graph of f of x, y equal to f of x. Now what is our interest? Our interest is to find the point where f takes 0. We need to find a so that f of a equal to 0. So we would like to approximate it. So like earlier using intermediate value theorem. So using intermediate value theorem we can find a root, an interval in which the root lies. Let me use some psi here because I am using a comma b for the interval. For root leaves. Right. So now you find an interval a comma b where the root is. It means here f of a to f of b is negative. It means what do you know? There exists c between a comma b such that f of c equal to 0. Now our aim is to approximate this c. Alright. That c is nothing but our psi. So now let me assume that the point A is here and the point B is here. Okay. So here the idea is to join these two points. So the a comma f of a. So a comma f of a is the point of the graph. Similarly, this is b comma f of a is the point of the graph. Now what you do is you just join these two lines. Is what I am doing. I am drawing a secant line joining these two points a comma f of a and b comma f of a. Alright. So now our first approximation to the root is nothing but where the secant line intersects the x-axis. That is our first approximation. That means x, y-axis. Okay. So this is the original root and our first approximation is x0. So what is x0? So x0 is a point of intersection of secant. Okay. So now what is the equation of this line? I hope given 2 points, let's say x1 comma y1 and x2 comma y2. I hope you know what is the formula for a line joining these 2 points. Okay. So what is the formula? So that is y minus y1 equal y2 minus y1 by x minus x in x minus x. Correct. This is the one, right? So now here it is. Now the secant line is nothing but y minus y naught. What is y naught here? If I compare this one is x1 and y1, x equal to y minus y1. So that is y minus f of a, which that equal to the other guy y2 minus y1, that is f of b minus f of a, right? B minus a is into x minus. Alright. So this is the equation of line. Where is that line? Line is. Alright. So equation of the line we wrote it there. Now I need to find a point where it intersects the x-axis, right? It intersects x-axis means so the y must be equal to 0. Isn't it? It intersects x-axis. So if it intersects x-axis, so y must be equal to 0. Alright. So make y 0 and try to find what it is. Okay. So you will have b minus a. Substituting y equal to 0 in there. Substituting y equal to 0. You send this b minus a to the other side, so that minus b into f of a. Right, on the other side, what this makes into x into f of b minus f of a. F of a minus a. We get the same thing, f of a minus a. Right. So now on both sides, you can actually find a into f of a and minus into minus plus a into f of a. So these terms will get cancelled. So if you keep x one side and send everything to the other side, you can find that x equal to what is it? So x you keep it this side. In the denominator, obviously you will get f of b minus f of a. This will be everything up. And whereas in the numerator, so a into f of b minus b into. Right now, this is the initial approximation. So in bisection method, the first approximation is just midpoint of the interval. It is so easy to calculate. But here, the first approximation is the point where the secant line intersects the x-axis. Okay. And yeah, it involves some computation because you need to find what is f of t. You need f of a, and everything you need to substitute here. So computationally it is costly, but the other way if you see the rate of convergence, I mean if you compare with the bisection method, if you get some accuracy at 100 steps in the bisection method, you may get the same accuracy here in the 5th step or maybe in the 10th step. It means this sequence whatever we are getting here, I mean initially you get x1, so the next approximation you will get x1, the next approximation x2, and so on. We will get in sequence 2. So we want the sequence to converge to a root. Alright. So now suppose if you take x10, so the distance between the exact root and x10. we may get here less than 0.01 or 0.001, but whereas in the bisection method we may opt in the 40th step or maybe 30th step. Alright, So let us quickly solve a problem using this. See, after finding first approximation, what is it you need to find the next approximation? So let me explain that also. We found the first approximation now, so x naught. So you see what is the function value here. So that is x naught comma f of x. Alright. So initial interval is a comma b, right? Because you know f of a is positive, or f of a is negative, and f of b is positive. That is why this interval a comma b is. Now this time you see what is the sign at x naught. So a and x naught is somewhere here. Need not be a hidden point. So it is we are not biased. So here it is negative, and here it is positive. And we found here it is negative from the graph, and I'm seeing it from the graph. It is below the y-axis. We are treating it. So the next interval is going to be x naught comma. Why? Because at x naught coming x equal and b x positive. So in between that 0. Alright. Yeah. Any question? Please someone raise hand. So the new interval you got it. Again, you do the same thing for the new interval. What I mean, again you construct the secant form. Now you see where it intersects the x-axis. Right. Now this is what going to be our second approximation. This is okay. So now you see earlier the distance between x naught and the root. Right. Now you see the distance between x1 and the root. It got decreased. Okay. Again, what do? Again, you see the value of x1. Right. Now you draw the secant. Now the next approximation x is. So this is how we proceed step by step. So it is like the bisection method. Bisection method only there, but we are not taking the function values. We are just seeing whether it is possible. But to calculate xi here, we need to use the function. Especially this formula we need to use. This is the formula for the regular function. Okay. So let me write the formula. Again, xi, the formula for xi, whatever interval you're taking, a comma f of a comma b, so you take a into f of b minus b into f of b by f of b minus a. So this is the formula you need to write for regular function. False position method, you can say false position method. Now let's do one thing. Let us solve a problem using this method. So let me do one thing. Let me take some equation. First of all, so the question is to find approximate root of this one. F of x into e power x minus 1. So find root of this guy using Regula Falsi. So that is our question. So what shall we do? Initially, we need to look for an interval where the root is. Alright, using intermediate value. So you go for trial and error. F of 0. What is f of 0 here? 0 into e power 0 minus 1. But 0 minus 1 is negative 1. So let me see what is f of 1 here. 1 is nothing but 1 into e power 1 minus 1 is e minus 1. And I hope e value is 2 point something, so it is greater than 1. So e minus 1 is greater than 0. Right, we are lucky. So in the first two steps we got. Suppose if you have a function for which f of 1 is also negative, what you have to do is, so I hope you can see the screen. So now, like earlier, here we'll create a table. So let's go first. So I'm going to take serial number, and E, B, the interval where the root lies. And here, yeah, you better write f of E and f of B so that you can use it for computation. Or no matter if you don't write much. Okay. So here you write what is x naught. So x naught, right? Or you better write it like xi E f of B minus E f of B divided by B minus f of B minus f of B. This is what x is. Alright. So later you go up to write what is f of x, because we need to know its value and know its signature to decide what is the next. Right. So initially, the initial step I take the interval 0 and 1, because there the root lies 0 and 1, and f of 0. What is f of 0? I hope you can see that it is minus 1. And f of 1, which is actually e minus 1, better write it down. So you calculate what is x. So what is x now? So that is e into, so a is 0. So 0 into f of 1 minus 1 into f of 0, 5. Divided by, you need to write f of 1 minus f of 0. Alright. So if you compute it, 0 into f of 1 anyway that becomes 0 minus, and you know what is f of 0. F of 0 is anyway right. F of 1 is e minus 1 minus f of 0 is minus 1. So finally what we found here is 1 by e. Yes, 1 by e, because it is minus plus. So it is just 1 by e. Okay. So you compute what is 1 by e value. You may take it up to 5 decimal places, depending upon up to how many decimal places they ask. So generally in the question, you may be asked find root using regular Falsi method up to 4 decimal places, okay, or 3 decimal places. So if they say 3 decimal places, minimum you take 5, and later you do the iterations until you get 3 decimal places a week. That's what it means. Find root correct up to 3 decimal places means you need to do those iterations until you get 3 decimal places a week. What I mean, for example, we get in the first iteration we found 0.123, in the second iteration we found 0.127, 1, 2, 3, 4, 127, 1. In the next iteration we found 0.1272. Next iteration 0.1273, 0.1273 remains as it is. Now, up to 3 decimal places, I am sure that the root is 0.127. Okay. So 1 by e, now what you have to do, you need to see what is f of 1 by e value. So is it positive or negative? F of 1 by e. So the function is, x into e power x minus 1, that is e by e, e power 1 by e minus 1. Use calculator. For regular Falsi method, you must carry a calculator. Physically, Is it positive or negative? Is it positive or negative?
Negative, sir.
So you're saying it's negative. So you better write its value, okay? Because we need to know its value. So in the next calculation we are going to use it. So anyway, it is negative. So the next interval, at origin it takes negative, here it takes positive value. Therefore, so the next interval is going to be, since we got negative here, the negative one only I need to calculate. So the new interval is 1 by e comma 1. So now you need to write what is f of 1 by e, right? And f of 1. And using it to calculate x one. N of the right. Second one is the new interval is 1 by e. Here it is negative. It is not, here it is positive. So you see what is f of 1 by e. Okay, and you write what is f of 1. Then you e minus 1. And you calculate x1. Now the formula for x1 is going to be a into, that is 1 by e into f of b minus b into f of b whole divided by 1 by e of f of b f of 1 minus f of 1. Alright, so you will find the next approximation. So can you tell me what is x1? You tell me what is the value of x0 also, 1 by e. Come again. 1 by e.
Minus 0.46853.
See, I'm asking 1 by e value. If it is 1 by e, why do you get minus?
Function value, sir.
I'm asking 1 by e. Yes, 1 by e. Because I want to know x0. I'm just asking 1 by e.
0.3678.
0.36. You better take one of these also. What is there after e?
Eight seven, sir.
87. The next number is less than 1. I mean less than 5. But is
No,
less
sir.
than 5.
9, sir.
Okay,
9, sir.
that means you round it to 5 decimal. Better right now. Okay, so if you are cutting a decimal, you know how to cut, right? How to round it. The number, the last digit, if you want to cut up to 8, after 8 you see the last digit. If it is more than 5, you add 1, 3, 4. If it is less than 5, no need. You can write the, I can see that. So what is the x1 you get here?
0.6839, sir.
0.68.
Sir.
x1, you're saying x1 only, no?
Yes, sir.
See, okay, so if we want, see, if you observe that the earlier is 0.3678 and now it is 0.68, when the first decimal places itself are not equal here. So you do one thing, you better calculate x2. Suppose if you're asked to find root of two decimal places, you need to compute these xi's until you get two decimal places. Okay. So here let me explain the problem which is there in our reading material. this is the problem. Same x into e power x minus 1 equal to 0. Now we can see it on the screen. And root of an equation x into e power x minus 1 equal to 0 lies in the interval. They gave the interval. Now there is no necessary necessity to find f of 0, f of 1. So they gave us it. So determine this root correct to 3 decimal places using regular Falsi method. So now the initialization is done with this a comma b. So we are not free to choose the initialization. So they already gave us. So we have to start with this a and b only. At least earlier I started with 0 and 1. It's fine. Okay, they asked us to start with 0.4. And if you see the steps here, so I'm taking a and b and they are taking it as x not an x. So the interval in the formula we are taking a and b. So they are treating that as the x not and x. So it doesn't matter whether you treat it as x not x or a comma. You must be correct with the formula. Okay, and with this x not and x1 you make it confusing. Better follow a b formula. A into f of b minus b into f of b divided by f of b minus f of b. Both are same, both formulas are the same. Okay. So here you see x naught and x1 they rotate and they computed what is f of x1 and f of x2 and finally computed what is x2. So that is 0.54637. Okay. Now you see now we need to see what is the function value here. Alright. So if you see the function value, so function value is negative. F of x is negative. So we know at 0.5 you can see that the function is negative and at 1 it is positive. And in between we got x naught. Maybe here they are writing it as x. So at x naught, okay, let me write x2 only because we may get confused. So at x2 the function is taking negative value. So our new interval is going to be this. So our new interval is updated to 0.54637. Okay, now this is what our a comma. Alright. So now if you go for the next iteration, so here it is. So the next iteration is this. So we can find f of x1 and x2 is equal, therefore this is the updated interval. Now use these updated values to find the next one. Right. So we found it is 0.5607. Alright, so x4, x3 is this and x4 is 0.561. Now you can see two decimal places are equal. Maybe we go for some more steps. So this is x5, right? So x4 is this. You can see the x4. Yeah. And x5 is 0.566. So similarly, you will go until the three decimal places are equal. So this is what x6 you can see. And let me show you what is x5 here. So x5 here. Okay. So this is x5. And you see in x5 the number of you have 0.566 and here also 0.566. So three decimal places are equal. And suppose if I round it here, it is also 0.567 and here also it is 0.567. Therefore, the root up to three decimal places, correct up to three decimal places is 0.56. For the equation, what is that equation here? X equal to x minus 1. So for this equation, this is the approximated root. I am not saying that when you substitute you will get 0. The value will be near to 0. Since it is an approximated root, that's it. It's not the exact. But if you take the exact root and if you see the first 3 distinct places, we can guarantee that these are the first 3 distinct places of the exact. Right? So this is what Regula Falsi. But anyway, I thought of discussing the Newton transfer also. It's not possible now because I have class for the physical also. So I need to stop here. Alright. And do you have any questions or doubts?
Sir, in bisection method, how to find when there is multiple roots? Sir?
What do you mean? Multiple, is it a root with
Common roots?
multiplicity?
Yes, sir.
Okay. It's like the repeated root.
Yes, sir.
If you have repeated root, bisection method won't help us.
Yes, sir.
Because in the bisection method, every time we are finding an interval, it gives the rootless. Suppose if it is a repeated root, and if the equation is a kind of quadratic equation or an even degree equation, then it's not possible to find an interval also. Okay. But in some cases, even if you have a repeated root, maybe you do one thing, think of this guy. So if I have f of x is equal to, let's just take an example, x minus 1 whole square in x plus 3. And you know the roots explicitly. Okay, the roots are 1, 1 and minus. It's very clear. But if I want to use bisection method and if I want to find the roots, maybe this one it will not it easily, but to find the other guy. So let me take a line and the points here. I hope you can actually tell where this function is positive and where it is negative. Alright. So this guy is always positive, whatever be the value of x. So this is always positive because you have square. Now it all depends on this point only, minus 3. So if x is after minus 3, okay, then definitely this guy is positive. So here it is. Alright. Whereas if you are before minus 3, it's like minus 4, you take like minus 4 plus minus 4. So in that case, it becomes negative. You understand? So here,
Yes, sir.
we can only find the interval for minus 3. Okay, but we can't find an interval for 1 here. But still, by looking at the function, you know, okay, it has what is it? Multiplicity. So the disadvantage here is if you want to use intermediate value, when it has a multiple root, intermediate value won't help us much. You can't find a root in which root lies. You can't find an interval in which root lies. Because there is actually a root at 1, but you see, the left side of 1 it is positive, even if the right side of 1 is not positive. Okay, so bisection method is not suitable for the roots with the co-multiples. If it has other roots, yeah, for that it is fine. Like let's say here, we don't have an issue with finding approximating minus using bisection. And also
Is there any
one more, there is one more disadvantage with bisection. May not convert. Suppose whatever interval we start, further if you is not a midpoint of some interval. So it's never going. We won't get the exact. You understand what I mean? For example, you see in this case, suppose if your interval is -4 and the midpoint is -3, then easily identified. Alright, whereas if I start with some interval here, okay, if I bisect these lines, I found that this -3 never be a middle point of any interval. Let me assume. And in that case, yeah, the accuracy you're going to get fine. The accuracy is going to be increased step by step, but it converges to the root very slowly. That is what is recorded by step. Even this regular falsi method, it is computationally costly. This one is computationally costly because every time you see, you need to compute f of x4, f of x1, you need to substitute everything here. Computationally, it is costly. Okay. So there is one more method which makes our life easy. Okay, that even the other method is not going to help us find one, but it can help us in finding the root more faster compared to these two methods. Compared to bisecting the regular falsi. Any more questions? Is your question answered?
Yes, sir. Okay, sir.
Any more questions? Right. So we'll meet tomorrow. So tomorrow I'll call you to cover Newton Raphson and also finite differences. So that we'll have just one more class to find out the results. Okay. So I'll stop it here.